I'm going to talk about AI and how much it's going to cost. As was pointed out to me earlier, for both public relations reasons and competence reasons, I'm not going to discuss the social costs of AI. We also don't know those yet. So we're actually talking about the money costs of AI. So here's the agenda. So I will say AI costs, they're big. I mean, you won't believe how vastly, hugely big they are. Sorry, apologies to Douglas Adams here and to you. I'm going to do a quick intro. We are going to have the minimum amount of accounting and finance necessary. It's going to be a little bit. I'll try to motivate it for why you think we should talk about it. I will not succeed at that because we are nerds and this is accounting. So I'm just going to do my best. It's going to be okay. We're going to get through it. I will talk about generative AI and what the heck we think is going on here, if anything. Specifically, try to look at some of the most important elements of large language cost modeling. And then I'll make stuff up about the future. Anytime you see people make predictions about the future, it's always made up. I'm just more honest about it. Okay, so hi, I'm Todd. I started ML SRE at Google and did a bunch of like ML reliability stuff at Google for years before that. Now I have the weirdest job. Do you know those jobs at big companies that either are super cool because they figured something out or are themselves a symbol of that company's dysfunction? That's my job. I don't know if it's perfect and clever or if it's just kind of weird and nobody should have it. Anyway, I am part of the engineering team that reports to our chief financial officer. So our finance division has a very small engineering team, and we mostly mediate the impossible task of communicating between finance and engineering. The language is different, the understanding is different, the coordination and communication is different, and often they are unable to talk to each other. You may have had similar experiences. You may be causing similar experiences right now. So that's what I do right now. I think you all, so I always sort of start with the hypothesis of who are you? Like, why are you here? The only things I'm assuming is that many of you are paid to do some sort of reliability engineering, and you're curious about this big transition to artificial intelligence. All of those elements, paid and transition to AI, are super important. The paid part is why you will care about the costs, because the AI costs have the possibility of removing most of your future pay. So if you care about your pay and you've heard something about AI, you probably want to notice just how much your company is planning to spend on AI, because I don't know about you all, but mine is going to spend a lot. So that's why you should care about costs. We're going to talk about accounting and technology and some other stuff. And the question that I won't answer, I mean, I will answer, but you already knew the answer is this AI transition going to change everything? And the answer is, of course, just like everything else has. It will also change everything. So is it going to change everything differently? Which is the question I think most of us really have. Don't know. Not too sure. OK, so I'm going to start with 3 questions. We're going to talk about how corporations think about money. We're going to talk very briefly. I'm assuming most of you have played with Midjourney and ChatGPT, but I'll talk a little bit about what generative AI claims to be for and where it's going, roughly how it's used. I'm going to try to explain why it costs so much and why many of those costs are ineluctable in some ways. I'm going to try to predict what's next, and of course, an almost fanatical devotion to the Pope. Those are my 3 things. So let's talk about how corporations think about money. Just for a minute. Again, it's going to be okay. We're going to get through this together. It's going to be okay. Okay, super important disclaimers. I don't know anything about this stuff. I have no training in this stuff. I would be happier here talking about Wittgenstein's skepticism about meaning than I am talking about depreciation schedules. I promise you. So what that means is that you should not rely on anything I say about money and how it works for anything. And if you do, that's on you. That's not on me. I barely rely on things I say about money. Separately, it's super important to note, especially in this context, different countries think very differently about money in very specific circumstances. And so if you have an actual question about how your company thinks about money or how your organization thinks about money in some setting, you should talk to a professional who knows those things, because there are these, what are they called, laws that govern how that stuff works. And there are also professional standards that determine these things, and they are published, and none of us keep up on those. Just as you have not read every RFC, none of us has read most of the accounting standards. So just be aware of that stuff. Okay, so accounting is wild. Okay, so we're in Venice in the late 1400s, and Venice is like the European center of commerce at that time. Many roads coming in, coming out. There is a whole economic, socio-political, cultural reason why commerce is going down in Venice, but commerce is going down in Venice. Like, Venice is really active. At the time, most of that part of Europe was still using Roman numerals. Now, Roman numerals are wild, right? Because it's actually a lot more like a natural language. It's like if you spelled out numbers in your native language. It's fine, but you can't do anything with it. You can't move things. There's no positional value. You can't carry numbers. You can't line them up in any way. It's just a string of characters. And so if you add 3,212 plus 5 in Roman numerals, it's just a disaster. And so what was happening was people were writing things down. People were accounting as if it were a journal, as if it were a private journal of their thoughts. They would just write down linearly, but with no way to add things up or check things. And so then they would sell things all day and then go back and look at how much they had and then sell things the next day. Well, that's not really accounting. It doesn't do any good. You don't really have any books. So this guy comes along, Luca Pacioli, and Luca Pacioli he's a monk. He's a mathematician. He is an educator and a writer. He's also a close personal, and some say more than friend, of Leonardo. And he writes this amazing text that covers all this stuff. And buried within it are two fascinating things. One is dual entry accounting, which had started to be used in Venice around that time. And the other is the math to do 2D representations of 3D things in the world, which shows up almost immediately in the Last Supper. So from Luca here, Pacioli, we get the Last Supper and dual entry accounting. And I think those are two things you didn't think were going to happen in the same slide today. So there, this is probably the best it's going to get at this point. Okay, so what do we get? So, I can talk a little bit about accounting, the details, but actually most of it doesn't matter. Dual entry accounting is important and interesting because pre-computers in particular, it gives you a way to check that you did your sums right, that you didn't leave anything out. And even post-computers, it gives you a way to detect fraud because you are, a simple example would be you write down all your sales on the left-hand side and you write down all your inventory reductions on the right-hand side, and the left-hand side should predict how many widgets you have left. And if you have a different number of widgets left, you should know what happened to them. And the widget should predict how much money you have. And if you don't have as much money as you no longer have widgets, then something happened to the money. And so this is a relatively straightforward idea, but it turns out to be enormously powerful. But I'm not going to talk about that any more than that. What I do want to talk about is say, what is accounting for? Accounting is for stories and for trust. So it helps us understand both our own organizations, how they work, what's happening and what's going to happen to them in the future, but also helps us understand other people's organizations. And when a society, this sounds like, it sounds like glorification of accounting, which I do feel bad about. I'll still be honest with you. But when a society adopts common standards for keeping track of these things, it makes it possible for example, each of us to go take a new job. Right? You take a new job, and one of the things you rely upon when you take a new job is that the company has money in the bank and that they will be able to pay you. And you actually have a way of verifying that, and that if it's a publicly traded company, we all have a way of verifying that. The fact that it's so public and audited and covered means that most of us don't verify it. The understanding ourselves part is mostly what I'm going to talk about now. So we need ways of tracking how much money we're spending, but spending money is weird. Some of the money we spend is just gone. And some of the money we spend gives us stuff that's useful for indefinite periods of time, actually definite periods of time. I'll talk about that in a second. And so it's very different. And we're going to talk about that in a second. So let's look at the bare minimum facts. I think you only need a few things to understand the whole rest of this. So one is accounting versus finance. Accounting is keeping track of stuff, and finance is analyzing and predicting it. That's fine. Show of hands, how many people here know the difference between CapEx and OpEx, or capital expenditures and operational expenditures? That is like a solid 30% of the audience. That's really good. That means somebody asked you to analyze the cost of your fleet at some point. Yeah, so that's good. The rest of you will have to figure that out at some point, or not. I mean, find jobs where you don't have to, because, man. So operational expenditures are things where you spend the money, and it's not that, I don't want to say it's gone, but whatever you were going to get for it, you got for it now. So a good example is salaries, right? If you pay someone money, at the end of the period that you paid them money, they don't owe you anything. We've noticed that companies feel that way, and perhaps we should as well, right? Like, the period ends, and now we're in a new period, and if you pay them more money, then they'll stay for that period as well, and that's the relationship there. Rent is the same way. Utility bills are the same way. Paying last month's water bill does not give you water this month. This month's water bill is for that. So that's operational expenditures accounted for within the period. Capital expenditures are, you get a thing, and it's useful tomorrow, and it's useful next year, probably. And there's this question of how many years, and we'll talk for a second about that. So if we buy, the example I have here is if we buy a $48,000 server, but we think that we can, and I'm talking about how depreciation and amortization work. If we buy a $48,000 server and we think it's useful for 4 years, the standard way we account for that is that server costs us $1,000 a month. Now we're out $48,000 of cash, and that's a different problem. This I find most of us as individuals are like, wait, those are the same, like in my life, those are the same problem. They're like, no. Company's life is like, cash comes in, cash goes out. Totally, in some ways, disconnected from how much this month cost us, right? So if we spend $1 million on things that will be useful for hundreds of years, this is a very cheap month, but also we're out $1 million, right? So the amortization and depreciation, those are the period over which we claim the thing is going to be useful. Just to make sure people got that, different things have different amortization schedules. A house is useful for longer than a car, is useful for longer than a computer, maybe not anymore, maybe. And different kinds of computers are useful for different kinds of times. This is a super important point, because I think, again, depreciation is about predicting the future, and we're going to discover in a hot second that that's not that easy to do. So let me do a concrete example. How many of you remember when we used to just only use plain text on the internet and everything was grand and it was fine, right? A bunch of old folks like me sitting around, that's good. It was terrible, right? It was terrible. We had Telnet, for God's sakes. Oh my God. And also HTTP, it was fine. So the web was blowing up, the year is 2000, we're gonna ramp up to this .com hilarity, everything's great, right? We buy relatively cheap at the time servers, and they can do, and these are spec numbers, so they're definitely big variation here. So the numbers themselves don't matter that much, but they're within a range of historically accurate. They could do, let's say, 500 plain text HTTP requests per second, like on a kind of cheap ass computer with, Apache that's forking a process on every single receive accept. Like, I mean, this was the way. We didn't have pools. We didn't reuse sockets. It was an innocent, different time. It was just bad days. Anyway, so we had that. So that's fine. Somebody comes along and says, if people are going to spend money, they probably don't want their credit cards on the internet. And I'm like, we can barely route the packets. You think someone can look at them? But anyway, it was a sound point. It was really good. So we're like, okay, we're going to encrypt stuff, right? So on those same machines, instead of 500 plain text HTTP requests per second, we do about 5 SSL. Like, SSL had just come out. All the processors were terrible. Like, we do 5 requests per second. Maybe a little bit more, maybe 6 or 7, but certainly not 50. No way. So people are like, okay, well, so wait a second. So 500 plain text HTTP requests per second, that's about 0.4 cents per request. I think, as long as we're doing anything useful with it, that's actually pretty expensive nowadays, but it's okay, we can do it. It's fine. All of a sudden, this goes quite a bit more. This is very bad. $40 per, yeah, you're right. Should I edit it live? No, yeah, you're right. I'll fix that, I'll fix it in post. So if we have a website with 300 requests per second, all of a sudden we go from, we're gonna have some spares and stuff, but the numbers blow up ridiculously quickly, right? So that's not what we're gonna do. So realistically, there are 2 paths we can take at this. So one path we can take is we can only encrypt a few things. And that's in fact the path that most companies took. They're like, okay, all the shopping experience is plain text, and we'll bump you to an HTTPS connection on checkout where you provide your payment. This was awkward from a web application perspective. It created all kinds of UX, UI problems, but it saved us from any significant amount of HTTPS traffic. The other approach that people who really wanted to encrypt all their traffic was they just bought accelerators. There were like people marketing these PCI cards that all they did was accelerate SSL, TLS. And you're like, okay, that was another thing, and that significantly reduced the cost of those. But here, so insert yourself into this moment in the past. Like you're sitting there in 2000, you're advising, you're about to roll this out, and you're looking at the finances for this. The real question is, if those cards, and I looked at historically, like what those cards costs, like that, there were different prices for them, but they were typically, moderately expensive, certainly much more expensive than the servers themselves, in the sort of, depending on the capacity of them, $6,000 to $20,000 per card range. You're like, that's a lot. And they didn't offer that much more capacity, but they did more. So the question is, super important question: how long are you going to need those cards for? Because if those cards are good for this month, that is a terrible plan. Do not do that. That's a really bad plan. But if those cards are good for 10 years, it's so cheap you should just buy all of them, right? And obviously neither of those is the right answer. But the right answer involves predicting the future. Because one of the things that happened was, Intel and AMD made their chips do encryption a lot better relatively quickly, not as quickly as any of us would like, but sufficiently quickly that by the time we hit the post-dot-com collapse, encryption acceleration was kind of a lost market. It just went away. People still built like special purpose SSL concentrator hardware, but not that big of a deal. Okay. So this is what I really want to talk about, as the dark art of appreciation, right? So houses, typically 37 years. It's really 27 and a half years in most jurisdictions, and I have no idea why. No idea why. And the assumption is not that your house is gone after 27 and a half years. Of course, even though I live in the United States, like my house is 120 or 130 years old. So it obviously, but much of it has been rebuilt over that period. So the idea of this is not the life cycle of something, but the economically useful life cycle. So like all your friends who have like goofy little computers from the 2000s, you can turn them on. They're just not useful for anything real, but they're fun to play with. But that's it. We're talking about the economically useful life cycle. Where we are in ML, and I'm going to talk about this in a second, is that we really don't understand the depreciation cycle of accelerators. They're insanely expensive, and we just don't know how much people are going to need them next year, and the year after that, and the year after that. And so that's really the problem that I want to talk about for the most part. When we have new technology, we typically misestimate the depreciation because we're just predicting the future from insufficient data. So, okay, we're going to set the money aside for a second. We'll come back to the money a little bit later, but we'll set the money aside. So generative AI, how many of you have used ChatGPT so far this particular talk? Sorry, I'm feeling like I'm typing right now. All of us have used ChatGPT and or Midjourney and or one of the various things, right? So large models, they are usually trained on language samples. There's bias in those language samples, of course. And all they're doing is learning very complex conditional probabilities among language snippets. One of the things I think brings this home for most of us most viscerally is when you understand that all the URLs are generated as well. So if you ask a question to a chatbot and the question involves producing a URL, the URL will be a generated URL. There's a chance that's a real web address, but that chance is actually unrelated to the process by which the URL is generated. The URL will look good, and it will look like a real URL. It will look like a real URL from the site that the URL comes from, but it may well not be an actual URL that has ever existed. And once you sort of understand that, for me, that worked really well, because I was like, oh, and everything else is just like that too. Everything else is like that. And so you're like, okay, so it really is just, I have an A. Should I have a B or a C or a E? What should I say now? N. A-N, almost always followed by D. A-N-D, look, I'm going to need a space, right? And that's what's happening inside of these models, and the tokens are obviously larger, but yeah, so URLs completely made up. And yet, These things can understand language, so they give the appearance of having context and understanding what we mean when we talk, because it turns out maybe what we mean. I mean, this is I have this theory that the reason we are all freaked out by this is we have the sneaking suspicion in the back of our heads that we're just probability engines as well. And we're not gonna, that's the different talk, that's a different talk. So the ability to understand language is going to likely revolutionize many of our human-computer interfaces. So like, we have SQL and we use SQL to interact with structured data. We have APIs that we use to interact with unstructured data. That's great. What if you could say, show me all the times that user traffic in the Berlin POP was higher than user traffic in the New York POP for requests to the new application on Tuesdays. Like, now certainly any of us, given enough information and enough context, could write that query, but what if you just didn't have to? What if that was actually what you wanted to know and you could just say it? Now, the next thought all of you should have is which parts of your job are about to be obviated by this technology, because some of what you do is listen to words in a human language and translate them into words in a computer context. And so that part is going to go away, I think. LLMs can generate language, so that's pretty interesting. That's the thing that's getting the most press. I don't think that's the thing that will ultimately have the most impact, but I do think I massively underestimated how much we all hate to write. It is fascinating to me. I'm like, I don't think writing is that bad, but people really hate to write. And the killer application for all of these, like for ChatGPT, the killer application is first draft of whatever thing I don't want to write, please, right now. And so that's fascinating to me. And finally, like the one that hasn't gotten as much press outside of our communities is coding. Like first pass coding, it's pretty okay now, and it's going to continue to get better. And it's one of the areas where it is easiest to test for correctness, because you can compile and run a test suite against the code that you generate, right? And so test-driven development might start to look like you ask the AI to write the tests, you, human, validate the tests, then you ask the AI to write code that passes the tests, and that's your development. That's not that far out from where many of us are today. Okay, so why accelerators? This talk is about money. The money is going to accelerators. What are these accelerators? So everyone knows Moore's Law ended, right? Moore's Law is gone, super sad. Amdahl's Law, done. We got to the end of it. There's some limits. It's too bad. So what? Well, so what is that many of the services that we have come to rely upon are economically dependent upon Moore's Law. So if you think about consumer services on the internet, the budget for consumer services on the internet being bigger and better and cheaper next year than this year, that was Moore's Law. Moore's Law just paid for all of our lifestyle for the last 10 years, and now it's over and things are sad. No, things aren't that sad. But it does mean that if, that's a little bit of a subtle point I'll acknowledge, so I'm not gonna explain it here, but if you wanna understand it more, or you wanna argue with me later, I'll be happy to talk about it. But now that Moore's Law is over, we need to recreate Moore's Law in the small. So that means that big organizations like Google, like Microsoft, like Baidu, are gonna have to wander around their life and look for chunks of compute that are similar enough to each other that they can have a special purpose processor thrown at them. So that might look like video compression for some, it might look like network acceleration for others, and lots of people are doing network acceleration. Like, I mean, one way of thinking about TCP offload that has happened over the last, N years is it is a form of special purpose compute acceleration. Because in general, if we can put all these things in one computer that we're all comfortable with and familiar with and know how to reason about, that's simpler. We like that, right? That's easy. But we can't anymore. So those days are gone. We're very sad about it. And now we're gonna have computers that are really just collections of other computers, which are really just collections of special purpose processors. So what are the LLM accelerators? Well, like for general purpose machine learning, one of the things that happens a lot is a whole bunch of matrix operations. And it turns out matrix operations are acceleratable. It turns out like that's a very specific kind of compute. And if you design a chip that mostly does that, you either have a GPU or one of these other ML accelerators, like so Amazon has Trainium. God, I don't know if Trainium is unobtainium, but I love that name, so great. Google has TPUs, tensor processing units, and all of these things are just things that are not general purpose ALUs. They're just special purpose chips that only do a few kinds of operations. But those operations, they do dramatically more power efficiently and dramatically faster than a CPU can do. And they do that by sacrificing all kinds of things, but hopefully the things they sacrifice are not what you needed for that thing. So common ML tasks are much, much faster and more scalable. There's a little bit of questions about training and serving. How many people really understand at some gross level the difference between model training and model serving? Okay, that's a smallish number. Okay, so the basic idea is you make a model and then look things up in it. The process of making the model is training. The process of looking things up in it is called inference or serving. And they are in many systems, not in all AI ML systems, but in many systems, those are separable phases. That the training thing produces an artifact. That artifact is some offline representation of all of the stuff you've learned. And then you can load that into a set of model servers or a set of other software that will provide a network interface to look things up in the model. Both of these require special purpose compute, but very different kind of special purpose compute, right? So if you think about what happens at training is it reads some data, processes the data, thinks about the data, writes a set of changes to a very large distributed data structure, and then does it again, and then does it again, and then does it again. And so it is that process of reading a bunch of what it thinks the world looks like now, reading some new example or piece of information and updating that. Inference is really getting an example in and trying to compare it to what you already have. Okay, moving along faster. So LLM costs. The one thing that I don't think I said clearly, but I will say now clearly is, all these accelerators are ridiculously expensive. So like list price of an NVIDIA H100 is like $40,000, $40,000 for one card/chip. People use the term card and chip interchangeably because we really only care about the chip. It's not quite true, but yeah, so that adds up pretty fast. Like when A100s were roughly a factor of 10, not quite cheaper. But when you think about the Facebook talk about 2,048 cards, you start to put some numbers in perspective there. Like costs add up very fast. And that's why we care about this stuff so much. Okay, so what are the cost elements? Well, so the most important thing I think for you all to know is that compute dominates the cost for most of us. Now, in a number of presentations, you'll see like the network can be very expensive. Different people have used different tricks to try to drive some of the cost out of the network. Google published a super cool paper about a thing we've been doing for a number of years where we use a pure optical switch that is configurable to subdivide portions of these big clusters of accelerators so that we use less electronics and still have segregated clusters. But be that as it may, compute's the most expensive cost here. There are some storage costs. In general, those are not dominant because we've driven the prices out of storage for the last N decades. So storage is generally not dominant. The network is expensive, but the compute is still more expensive. Model costs are generally talked about in terms of tokens and parameters. Tokens are basically a word. It's not a word, and only people with a PhD in machine learning will tell you why it's not. It doesn't matter. Just a token is a word, but they don't want to say words, so they say tokens. There's some gatekeeping going on in this ML community, I'm telling you. Typical sizes of a number of parameters. So parameters are, you can think of them as the number of dimensions we're learning about at a time. So typical sizes of parameters that you may have seen range from 7 billion to 65 billion. So like Llama is rumored to have 170 billion Llama is 7 to 65 billion. GPT-4 is rumored to have, not confirmed, to have 170 billion parameters. So these are big things. One thing from a math perspective, training is very, very expensive. We can do some back of the envelope. I won't do it live because I'll embarrass myself. But all of us can later do back of the envelope. When Facebook says they have 2,000 InfiniBand switches, they have 2,048 A100s each in a machine, And they ran it for, they ran all of that training job for 3 weeks or so, I think they said. Like, you can start doing the math and be like, oh, wait, that's like, in terms of power, depreciated capital, the cost, that's very, very, very expensive. Remember something scary here. Training doesn't give you any economic return as a company, as an organization. All you have is an artifact you could choose to do something with. Facebook's choice was to give it away. So that's a different choice, but like, you could look things up in it, but the value to you, whether that value is economic or social or whatever the value function for your organization is, the value has to pay for all of the training. So unless you have something that's going to be very popular and useful to a lot of people, you better think twice about training a very, very big model. 100% of the training costs must be recovered in serving. There's lots of other uses we do. Remember, not everything's an LLM, but we're really talking about large language models for the most part here. So concrete cost estimates, ballpark for input data size, 1.4 trillion tokens. Llama from Facebook, training cost of, right there. I've estimated some of this stuff up. So it looks like if who knows, like obviously Facebook is not renting anything on the spot market, but we have spot market prices published. So we can get sort of it's not 1,000th of that, right? So the cost to train Llama 2 looks like, if it were on the spot market on AWS, it would be about, somewhere in the range of $15.5 million to train it. Like, I don't know, like a lot of companies here have a lot of money, but that's a lot of money, right? Like that's not something most organizations should just do without thinking carefully about it. There's some assumptions I built in there. So, that would be, if we assume a 30% experimentation budget, I didn't talk about that, but you don't know what to do until you know what to do, and you have to pay for the time it takes you to figure out what to do. That is probably obvious, but like you have to pay for that. Availability during the training run, I have seen numbers as high as 99% for medium periods of time and numbers as low as 0% for extended periods of time. Mary yesterday gave a talk about training data for models. One of the best ways to ruin your training budget is to train on data you didn't mean to train on, so you have to do it all over. Like if you train for 3 weeks and then you discover you trained on some of the wrong stuff that you shouldn't have trained on, the really right now state of the art is go do it again. So that's a 0% for those 3 weeks, right? You have nothing you can show for those 3, and that happens sometimes. So once you factor all that stuff out, it's probably closer to $1.1 million to train Llama 2. Like, still quite high, but I mean, like, we could chip in and do it, right? Like, it's fine. No, I do think it's interesting to think about like whether community projects are going to be able to do this. But here's the problem. Look at where this stuff goes. So Llama 2, when it came out, seemed like a pretty good model. Turns out, no. Turns out it's pretty small, because GPT 3.5 is somewhere around 150 to 175 billion parameters and probably costs closer to 5 million to train. GPT 4 looks like it's closer to like 1 to 1.75 trillion parameters and maybe costs closer to, I don't know, 13 to 50 million dollars or some published estimates. I have some links and when they publish the thing. So, and remember, you got to recover all of that cost plus the cost of serving if you ever train a model. Okay, so what about the cost of serving? Well, math, it's expensive. And it actually doesn't matter if it's expensive, because what we really need to have in our head is it's not free, and we've got this training cost we have to pay for. And so you start to really have to make some assumptions about, typical chat use cases, it looks like a single conversational round trip, depending on how you model the costs, somewhere between 0.5 cent and 7 cents per round trip. These are called conversational turns. Like, I don't know, that's not hideously expensive, but it's that plus the amortized cost of training. So you better keep that model around for a lot, but you can't keep that model around for a long time because everybody's training a new model and you need a new model. Your model has to be good, right? So this is the kind of environment we're in. Then there's serving demand. So if we I didn't mention fine tuning. All right, so there's a little parenthetical here. There's also fine tuning, so we're gonna have to pay for that too. This is one of those things like you feel like you're at the car dealership where you're like, you know, but there's also the undercoating and the special license plate, and there are a number of extra charges that appear. So fine tuning is the part where we take the pre-trained model and then we make it work better for some specific task. That's also not free. People are looking at ways to make it cheap, but it's not free. And in some cases, it's up to 75% of the cost of training the model in the first place. So not great. So basically, we're in trouble here. So if you look at, you know, something like a $4 million cost to train, and you know, I just took median numbers, $4 million cost to train and 3.5 cents per conversational turn, we're gonna need 100 million conversational turns or 100 million queries before the serving cost is 50% of the cost of the query. So you get 100 million conversational turns before your serving costs start to dominate the cost computation. So I guess my lesson is like here, if you have an enormously popular product, then you should probably hyper optimize for serving. Otherwise, you should probably use somebody else's model. So that's really where I want to go, and I'll wrap up really quickly here. So what does this all mean? I think on average, in the best case, you shouldn't train your own LLM. Like large language models are not for the weak of heart. Unless we see, and we could well, because things are changing pretty fast. So, you know, in the words of Ferris Bueller, you got to look around every so often or you might miss something. Things are changing pretty fast right now, and it's possible that we will be able to come up with novel techniques that produce amazing models with significantly fewer parameters or significantly less data. Or it's possible we could have a set of technological changes that makes the whole thing dramatically cheaper. Totally possible. All of that could happen. It's unlikely right now. And so therefore, unless you have a very, very special use case, a huge amount of projected demand for that use case, and a tremendous amount of money, I recommend against training your own LLM. So you should integrate, if your organization is looking at like large language model and you know, technologies, you should integrate some of the commercially available services. And you should rent accelerator hardware where you can. And the reason for that is I would let the cloud providers eat the risk of this, because like, you know, an H100 might be exactly what you need now and not at all what you need in 1.5 years. Or it might be, I don't know. Like we have had extended periods of time with relatively little hardware innovation, and then we have also had some very, very strange moments. So, them's my recommendations. Thank you. Any questions?